Okay, good morning, everybody. Welcome to the second day, module 2. On behalf of the two presenters, my name is Paralabos Gouliaris. I will present the first part of today's module, the groundwater modeling. And then Professor Sinead Muller will present the second part with the hydrogeochemical modeling. So, if some of you have already met, my background is in agronomy, with expertise in hydrology of groundwater and surface water. And today we will do the groundwater modeling in the coastal aquifers. So specifically, we will try to introduce the numerical models for solving problems of variable density flow and contaminant transport in the coastal aquifers. And in this morning session, we will see the connection of water resources management and modeling, the types of mathematical modeling for seawater intrusion, and particularly analytical solutions and numerical solutions based either on the self-defense approximation or the transition zone approach. We will also examine a case study. It's actually what we have to do before the mathematical modeling regarding the conceptualization, the conceptual model and data preparation, as well as how to calibrate the model and then use the calibrated model in management scenarios. And at the end, we will see some computer codes for modeling seawater intrusion. In the afternoon, we will try to set up together a 3D groundwater model, and then we will do a quick test based on what you will learn today. Normally, this lesson is for a week or something like that. So we will try to do it in 3.5 hours. So I will bombardize you with information. You can keep notes. There is at the bottom of each slide a number, and every 10 or 15 slides I will stop, and then we can discuss whatever you like if you have questions. So starting with the connection of water resources management and modeling. First, we need some definitions to put our lesson in context. So hydrology, one of the simplest definitions is that hydrology is points of water. So this is a quite simple definition, but covers also a wide broad area. So usually we split hydrology in subcategories. I will show you some of these categories. We have the hydrology of surface water, which is related to rivers, lakes, and also the relationship of rainfall runoff on catchments or basins. We have the hydrology of groundwater, which is related to aquifers. Similar terms are hydrogeology or groundwater hydraulics. Another classification of hydrology, very important, is the hydrology of the Vado zone, which is related to the soil moisture. It's not water, it's moisture, but it's very important because it is an intermediate link between surface water and groundwater. And similar terms are flow in the saturated zone or soil hydrology. We should not confuse hydrology with hydraulics. Hydrology is rather an environmental science, and hydraulics is a branch of fluid engineering related to water. Sometimes we use one term for the other, but they're not the same. Also, instead of water, we usually say water resources, which is actually a term used to refer to the management and use of water, primarily for the benefit of people. So the water management or the water resources management is related to water supply, to waste disposal, to lake management for recreation, to flood control, hydroelectric plants, and several other things that are related to anthropogenic activities or economic activities, if you will. So, however, the role of water in the environment is more important than just satisfying human needs. We have also to consider environment in the water resources management, for example, in terms of ecological flow in rivers or in terms of ecological water level in lakes or in groundwaters. So hydrology is closely connected to water resources management, but the successful management of water resources requires a solid understanding of hydrology. Hydrology is an old discipline, but recently, the last decades evolved, probably due to the need of the water resources management. And in the past, hydrology was dominated only by engineers, both civil engineers and agricultural and geologists, who actually would like to get some answer of how much water would be produced from a particular river, okay, in order to construct a dam, for example, or how much water a given type of a crop needed in order to estimate efficiently the irrigation dose, or how much water could be abstracted from an aquifer in order to protect some important boreholes in the aquifer. But society was on the move. Hydrology was involved into an interdisciplinary science, and now biologists, chemists, mathematicians, physicists, sociologists are involved with water resources management or hydrology or both. However, hydrology remains a quantitative science. It is an interdisciplinary but quantitative science. And mathematics is at the core of hydrology. We have complex partial differential equations that need numerical solutions. They can't be solved by an analytical way, as we say. And fortunately, the mathematical modeling, and particularly the numerical solutions, advances hydrology the last decades into an essential tool for the water resources management. So here we can see the simplified version of the hydrological cycle or the water cycle, which is actually a biogeochemical cycle that shows us the movement of water on Earth. So even if it's a cycle, it is convenient to start from the oceans. So the water with the energy of sun evaporates, and as the vapor are accumulated in the atmosphere, and if the conditions are suitable, have the condensation, and then precipitate the water on Earth. Part of this precipitated water transpirated from the plants to the atmosphere again, and the other part percolates to the ocean, and then the cycle starts again. So here is another more detailed presentation of the hydrological cycle. You can see that we have several components of evaporation from the oceans, from land, from reservoir, and as the water precipitates on the surface, part of the water surface runoff, we have the surface runoff, and another part of water infiltrate to the soil and recharge groundwaters. So if an aquifer is close to the ocean, is hydraulically connected with the ocean, the aquifer will outflow to the sea, but the sea will also intrude into the aquifer. And this is actually our subject for today, the saltwater intrusion in coastal aquifer. So from all these components of the hydrological cycle, we will discuss today the saltwater intrusion. So when dealing with exploitation, restoration, and management of fresh groundwater in coastal aquifers, the key issue is usually saltwater intrusion. Let's see some basic concepts. Probably you know that seawater is heavier than fresh water, since there are more salts dissolved in seawater compared to fresh water, so it is heavier. And as we can see here, we can see a coastal aquifer. From one side we have the fresh water, the other is the salt water. Between them is a zone of brackish water with an intermediate salinity, which is called zone of dispersion or mixing zone or transition zone. So in this coastal aquifer, since the seawater is heavier, it will be close to this mixing zone, will be downwards, and fresh water will be upwards. as we can see here. And also another important thing is that seawater has a higher density, actually different density and higher than fresh water. Since it is heavier, it has a higher density, seawater. But if we have the same system, the same groundwater system, saltwater and fresh water, then we should use the analysis in the hydrological or the mathematical analysis, the concept of the variable density flow that we will see in the next slide also. So if we try to give a definition for saltwater intrusion, it will be the inflow of saline water in an aquifer system. And as this saline water inflows into the aquifer, replaces the fresh groundwater that was originally in the system. So I think it's quite simple. But here we can see at this point that if we consider an equilibrium, either dynamic or a static equilibrium between the freshwater and saltwater, actually the saline water, the flow of saline water in the aquifer will be more or less equal to the outflow of fresh water from the aquifer. So they will be equal. But the outflow of fresh water can be either natural to the sea or abstracted by pumping. So if the abstraction is increased in a quite long time of period, let's say for the next 2 decades, this means that the volume of saline groundwater will increase and the fresh groundwater will decrease. So that was the physical concept, and then the next is to describe mathematically this concept. So we will need some basic physics, and particularly we can see here from the Bernoulli equation that the total energy of a fluid per unit mass is a sum of 3 different components. The first component is gravitational, fluid pressure, and kinetics. And you can see that these 3 components are with this term, first, second, and third in this equation, where G is gravity acceleration, as you can see, Z is elevation from a reference datum, P is the fluid pressure, the Greek rho here is the fluid density, and U is fluid velocity. So based on this equation, on the Bernoulli equation, we can have the hydraulic head, which is nothing more and nothing less than the total energy per unit weight of water. And given by this equation, generally in hydraulics, in surface hydraulics, groundwater hydraulics, and everything. Usually in groundwaters, we ignore the kinetic energy as the groundwater velocity is quite small. It's actually several times of order less than the other 2 parameters. So we have only Z and pressure with density and gravity acceleration. So the hydraulic head could be measured with a piezometer, as we can see here in this figure. This is a piezometer in groundwater, and the hydraulic head is the sum of elevation head and the pressure head, as we call this ratio here. And so sometimes we said instead of hydraulic head, piezometric head, they are the same thing. And or simply we can say just head. Okay. We said before that there is a difference in density of freshwater and seawater. Freshwater density is around 1,000 kilograms per square meter, and usually seawater density is not constant, but let's say for the Mediterranean condition is around 1,025 kilograms per square meter. So if the salinity in groundwater varies, so the density will also vary. Okay. And since density, the Greek rho here, appears in the hydraulic head equation, this could be taken into account and should be made before we use the measured head in a well or a piezometer, and before we construct the water level maps or compute the hydraulic gradient, as you can see the other figure here, between these 2 points, we see that the hydraulic gradient is actually the difference of head from one point to the other point divided by the distance of these 2 points. So this is actually the definition for the hydraulic gradient. So it's for the mathematical analysis for variable density flow problems, it is convenient, and we introduce a new term, the freshwater head, which is actually the head given by the previous situation, but instead of density of water in general, we use the density of fresh water, this rho 0 here. So before going on, we need to remind ourselves some key properties for earth material. So porosity is the percentage of a rock or a soil that is void and occupied by pores, and is expressed as the ratio of void volume to the total volume of the rock. The effective porosity is porosity available to fluid flow, usually might be lower than the total porosity. In some particular rocks. In other cases, maybe effective porosity and porosity will be almost equal. Specific yield is another very important parameter for a rock or a soil. It is defined as the ratio of the water volume that drains from a saturated rock or a soil due to gravity to the total volume of the rock. The specific limitation is a supplementary property of specific yield. As you can see, if you compare the two definitions, is the ratio of water that the rock can retain against gravity to the total volume of the rock. So from these definitions, we can combine them and we can say that the porosity is the ratio, we can have the mathematical expression, which is the ratio of void volume to the total volume, and it is also the sum of the specific yield and the specific retention. Another very important parameter for a rock or a soil is probably the most important, is the hydraulic conductivity. It is in units of velocity, as you can see here, and it is associated with the famous Darcy law and the Darcy experiment. So actually we have the Darcy velocity, which is associated with the hydraulic gradient, dHdL, and the parameter K, the hydraulic conductivity, which is a parameter related to the porous media and to the fluid. So this is very important, that hydraulic conductivity is not just a parameter of the soil or of the aquifer. It is a parameter that is related with the earth material and the fluid, as we can see from this equation, that relates hydraulic conductivity with the intrinsic permeability of the porous media and the fluid properties, like density and viscosity, which is this Greek M. Here we can see an aquifer, regional aquifer.
Grazie.
Okay. Okay, here we can see original aquifer. You can recognize the two most important aquifer layers that are usually found in a regional aquifer system: the confined aquifer and unconfined aquifer layer. The unconfined layer is on the top. We can see here the water table. Above the water table is the unsaturated soil zone. Below the water table is the saturated soil zone. The confined aquifer, in the confined aquifer, the water is under pressure. And we see here this confining unit that separates the two aquifer layers. Somewhere far away would be the recharge area of the confined aquifer. And the unconfined aquifer is recharged with fresh water from the top, from the soil infiltration, from precipitation and soil infiltration. You can see here some wells. Here is an artesian well, as we can see. A very important parameter here is a very important concept is related to homogeneity and isotropy in the aquifers. I don't know if you are familiar, all of you, with that. Okay, so we say that an aquifer is homogeneous if the hydraulic conductivity has the same value in the whole volume of the aquifer. So if it's different, we say that the aquifer is a heterogeneous aquifer. And another classification is that if the hydraulic conductivity is not the same in direction. So in a particular point of the aquifer, let's say this point 1 here, if the horizontal conductivity is equal with the vertical conductivity, since we have two dimensions here, x and z, so we say that it's isotropic. If it is if they are different, we say it is anisotropic. Is this for anyone? Okay, so how do you define this aquifer in this example with this value here? What kind of aquifer is this? That has a horizontal conductivity in the first point, 20 meters per day, in the second point, again 20 meters per day. But the vertical conductivity, the z direction, the direction of gravity, is 4 meters per day, also in the 2 points. How do you define it based on this definition? Isotropic, just anisotropic?
Isotropic on the main axis.
Exactly. It's a homogeneous because we have the same value of hydraulic conductivity, but it is anisotropic because we have different values of hydraulic conductivity in the directions. Okay, so it's a homogeneous anisotropic aquifer. Perfect. So some more properties related to groundwater. When we don't need a 3-dimensional analysis, so we usually use the concept of transmissivity instead of hydraulic conductivity. The two parameters are related with the aquifer thickness, B, and transmittivity is defined as the amount of water that can be transmitted horizontally. That's why we don't need a 3-dimensional analysis, by a fully saturated aquifer thickness under unit hydraulic gradient. So this is the concept of transmittivity. We're not going to use it today. Another important property is storativity or storage coefficient. You can see that this is a dimensional parameter. It is defined as the water volume that an aquifer will absorb or expel per unit surface area per unit change in head. So in the similar concept is the specific storage, which has units, which is the water volume that the saturated formation will absorb or expel per unit volume, per unit change in head. So for a confined aquifer, the storativity is usually taken as the product of aquifer thickness and specific storage, and is usually the order of 0.005 or even less. For an unconfined aquifer, since the water level rises, and so since the water level rises and the level of saturation is also rises or fall, we also involve the concept of specific yield here. And since specific yield is several times of order higher than the specific storage, usually storativity in unconfined aquifers is equal to specific yield, and it's quite higher compared to the confined aquifers. Okay, here we can see the role of modeling in the water resources management and in the decision-making process. So initially, let's suppose that we are manager or we are working in a team that is responsible for the management of coastal aquifer. and we have a problem, a management problem. Let's say that in our case will be a high salinity in some particular wells. But we have a salinity of 5,000 microsiemens per centimeter or even higher in some particular wells. And we have to solve this problem. So the first that we have to consider is to set the objectives of the problems, where we want to go. So how much will be the target of the salinity, for example, will be in these wells. Let's say that we would like to decrease the salinity in these wells to 1,000 microsiemens per centimeter. Okay, and then we need to think and propose some solutions to meet the objective that we set in the previous. And here comes the role of the model. We use the calibrated model. We run the model using as input data the proposed solutions that we have in the previous step, and we see the aquifer's response. We evaluate each solution, and probably we're making a loop between these steps. And then we choose the selected, the preferred alternative solution, and its implementation may begin. As you can see at the bottom is the monitor of the aquifer, which is quite very important parameter in the water resources management. And with the monitor, we can see if the proposed solution solves the problem. This is the way that we can see it. And also consider that if monitor wasn't there, we wouldn't be able to know the problem from the beginning. Okay, so here in this, we can see in this diagram how modeling and monitor can assist to water resources management. Here we can see some briefly some more details about the modeling process. We need the management information, field data, and then we set up the conceptual and mathematical models. And during the calibration and validation of the model, maybe a loop between conceptual and mathematical will be required. And of course, we don't have to forget that the model is a simplified version, a selected simplified version of the real systems and the phenomena associated that take place within it. I underline select because, as we can see, we have options which kind of model we're going to use, which is sometimes very important. So, in general, in mathematical modeling, we may use analytical solutions or numerical solutions. And particularly for seawater intrusion, the numerical solutions are usually based on the SARP interface approximation or the more scientifically rigorous transition zone approach. So these two approaches for modeling seawater intrusion are actually distinguished between them by considering freshwater and saltwater as immiscible or as miscible fluids. So in the former case, that they are immiscible, we assume that there are two separated fluids in the aquifer, the saltwater and freshwater, which are in equilibrium, maybe in a static equilibrium or a dynamic equilibrium. And in this case, we assume that the SARP interface, is developed between the two fluids. In the other case, we consider one fluid in the aquifer, which is water, with a variable salt concentration and thus variable density. And in this case, the transition zone is formed between the freshwater and saltwater. So the first attempt to modeling seawater intrusion is credited to Giffen and Herzberg, who independently found that saltwater occurred underground at the depth below sea level 40 times the freshwater head above sea level. Their solution is quite simple. First, they define the hydraulic head in this equation, the freshwater in the freshwater zone, and the hydraulic head in the saltwater zone with this equation, and taking as reference datum, we will show from here, taking as reference datum the sea level and making the mathematical calculations, they found that the location of the SARP interface with the letter Z is related with the freshwater head, H, above sea level, and the density of freshwater and density of saltwater. So for this very simple equation, if we have, we can predict the interface of the aquifer if we have the water level in several freshwater wells in our aquifer. After the Gibbon and Hilbert, there were more analytical solutions, either for confined or for unconfined aquifers, as we can see here. And if we focus in this solution for the oceanic island, we can see that if we have the recharge W on the top of the island, constant recharge, in an aquifer with constant hydraulic conductivity, K, from this equation we can find the freshwater head, HF, in a particular position of the island, and then we can find the sharp interface with letter C in the same location. So that's with minimum data, and with these two very simple equations, we can simulate seawater intrusion adopting the sharp interface approximation. There are more advanced analytical solutions in case of pumping wells. There are solutions presented by STAR or bearer diagram related to the upgoing cone below a pumping well. So that's all about analytical solutions, but I would like one more slide here to show you the pros and cons of analytical solutions. So one advantage is that they are very simple to apply, and also they are useful if we would like to get a quick answer or make an initial estimation before the numerical models. Also, analytical solution could be used to validate a numerical solution and should be used in many cases to validate the numerical solutions received from complex models. And the analytical solution was the only option when the computers were unable to run even simplified numerical models. Some disadvantages or limitations, if you prefer, is that analytical solutions usually adopt simplified hydraulic parameters, uniform hydraulic conductivity, for example, simply boundary conditions, spatially uniform and timely constant recharge or lateral inflow, simplified aquifer geometry. So we have uniform aquifer depth, and usually the solutions that we take are in steady state, solutions. So we take just the solution for each problem. We don't have the variation of time. And usually is adopting the sharp interface approximation, as we said before, although there are some analytical solutions that use the transition zone approach. So going now to the numerical methods, we need the numerical methods to solve the partial differential equations like groundwater flow equations, because they can't solve analytical for general boundary conditions. We can't solve analytical these solutions. So there are several numerical methods that actually they approximate the solution of the mathematical problem. So one of these methods, very common method, is the finite difference method that discretize the flow area with this orthogonal grid, as you can see here. And the solution in this flow area, this module area, we take the solution in the nodes of the grid by a system of algebraic equations. Another method that gives us more flexibility to discretize the model area is the finite element method or the finite element analysis. As you can see, we have the elements here and the nodes. Here we have triangle elements. but we can also have quadrilateral, or in three-dimensional, we can have pyramids, diagonal, hexagonal elements. And here in finite element analysis, we take the solution again in the nodes, as in the finite difference method, by solving the system of algebraic equations. There are also many other methods, like the boundary element method, or someone can use a combination of numerical methods to solve a particular problem. Another issue related to the numerical methodology is the spatial analysis. So usually in groundwater, we can assume that we have horizontal two-dimensional analysis or vertical two-dimensional analysis, and Z is the vertical direction to the gravity, or even use a three-dimensional, fully three-dimensional analysis, X, Y, Z. Here we can see the two equations for the sharp interface approximation. As you can see, we have two governing equations, as we say. One equation for fresh water and one for salt water. So we solve these two equations simultaneously for the freshwater head, HF, and for the saltwater head. And in this way, we may find in the aquifer the location of the interface, which is also obviously related to the recharge if we pump the aquifer and all the other hydrological parameters. In the transition zone approach, we also have two governing equations, but one is for water, the flow equation, and one for salinity, the mass transport equation. We solve the problem for the freshwater head, HH, and the concentration of salts, C. The advantage, the benefit using the transition zone approach is actually that we can have the distribution of salinity in the transition zone. So we can predict, we can estimate the salinity close to a pumping well. So we can estimate what is the salinity of the pump water, which is quite important. Some additional clarification in the transition zone approach that we should have in mind is that the water density and the viscosity depends on concentration, but we can easily take them from these two simple equations, the constitution equations. Also, the salt concentration is usually not measured directly, as you probably know, and we use electrical conductivity as an equivalent instead. And to address this problem, we can use the total dissolved solids to classify the salinization in water, and we can go from one parameter to the other, from TDS to electric conductivity, for a quite simple equation like this one. Another issue that we have to address in the transition zone approach is that we have to estimate the hydrodynamic dispersion as the sum of the mechanical dispersion and molecular diffusion. And for that, we need to assess the longitudinal and transversal dispersion and the coefficient of molecular diffusion, which usually is not so trivial based on the available hydrogeological data. And last but not least, we have to consider special numerical techniques in the transition zone approach, because they require to address the non-linearity of the coupled equation, because as we saw before, freshwater head and concentration were in the same equation, so it's more complicated to solve this kind of problem, and an efficient solver in the model is a must. So, I think we have realized that the heart of the mathematical model are the equations themselves, but what distinguishes each numerical solution extracted by any model are the boundary conditions. So, let's see what's the boundary condition. The boundary condition are the communication of the model with the outer world. So they are applied in the boundary of the model area, you can see here. And usually are known values of the dependent variables. Dependent variables are the head and concentration to our case. Okay. So there are three types of boundary condition. The first type, or the Dirichlet type of boundary condition, is applied when we know head or concentration as a constant value or as a function of time. And an example to apply this boundary condition is to the coastline, where we can apply that the head is the sea level, 0, or the concentration is equal to the salinity of the sea. Second type, is the second type of boundary condition, or Neumann boundary condition. When it is applied, when we know the gradient of the dependent variable, the gradient as they are defined from the first derivative here, which can be equal to a constant value or a function of time. And an example of the application of this type of boundary condition is when we know the freshwater inflow, the boundary of the model area, or also it is applied in an impermeable boundary at the bottom of the aquifer, let's say. The third type, or Cauchy type of boundary condition, is a combination of the first two types. And an application example is when we have a surface water body, a river or a lake, that communicates in hydraulic connection with the aquifer. Another condition, which is not actually boundary condition, although some people they define this as a fourth type, but it's not a boundary condition. It's the outflow or inflow from pumping or recharge wells in the aquifer. It's not a boundary condition because it is applied in the interior of the and not in the boundary. Okay, obviously, but some people they call them as a fourth type boundary condition. I think we are somewhere in the middle. I don't know how much time we spent or. Okay, we are in time. So we tried to cover a lot of things in a short time. I don't know if it was all familiar to you or if you need something to. If you have questions?
About the last one.
The last one. Okay.
The outflow is flowed from computers.
Excuse me, this one, please?
Yeah.
Yeah.
More about them.
Yes. Oops, sorry. Yes, it's we have the groundwater model. We have a volume, the groundwater model, and we apply in our model. We represent the thing that there is pumping wells. There is boreholes that pump water, extract water from the aquifer. So this should be included also in the model. Just that, yes, simple that. Or the other case, it may be inflow of water with some recharge wells. There are boreholes wells that penetrate the aquifer system, and we inject water inside. So it's a water inflow or outflow that should be included. Okay.
No, it's okay. It's just
Yeah.
like when I was applying some models, the wells or something, I don't consider that like another one. Just I have to find first ones, like so that's the reason because I was thinking that I have to make some changes or something new.
Okay. Okay. Yes.
Just to be clear, when I decide to use the sharp interface approximation or a transition approach.
Which is most appropriate?
Yeah, I mean, it should.
That's the question, or maybe I didn't understand well. That's
When I use one
When?
or I choose
Okay.
I decide to use one or the other one.
in the beginning, the scientists were used only sharp interface approximation because it was easiest to take a solution about that. So they make the assumption that there is a sharp interface between freshwater and saltwater. But what's happening in reality, in the environment outside, is that we are closer to the transition zone approach. Nowadays, to be honest, 95% is used only the transition zone approach because computers have power and we can have solutions based on the transition zone approach. So it is an old approach, but usually we discuss this as an alternative, like the analytical solutions. But in some cases, it wouldn't be so strange that someone would decide to apply the transition approach. Okay, I don't know if it answered to your question or it's confused you more. Okay.
It depends on the objective, no?
It depends on the objective, yeah. Let's say yes. In the second case, you need if you want to know from a model which is the concentration that pumped from a borehole, if you need this information from the model, you have to go to the transition zone approach. If you don't care about this and you need a quick answer, where is the interface? Is it 10 kilometers here, or it is, or you don't interested for details? Then you can apply an analytical solution based on the sharp interface approximation or a numerical solution. Okay.
Fracture and karst outcomes.
Fracture
And karst.
in karst.
May I use the same equation, or I have to add some corrections?
I'm not very familiar with the karst hydrogeology in general, but you can't use these equations as they are. So you have to use something more, probably, because the velocity is quite different. And yes, you need double porosity. Yes.
Yeah. Matrix structures.
Exactly.
And
But the concept probably is the same between the concentration and salinity and things like that, that you have to consider variable density approach also. We are okay? Okay, let's relax a little bit more. Let's see. A video that okay, I have prepared a video for you that relates actually modeling and water resources management. It tries to show us how important is modeling.
What is water modeling and why is it so important? What exactly does it mean? Well, imagine you're a traveller tasked with exploring and mapping uncharted territory. You're standing on a hill looking out over the horizon. The sun is high in the sky and the day is hot. Your water bottle is low. In the distance, you spot a body of water, but the path isn't clear through the hills and tree cover. How do you get from where you are to the water that you need without a map to guide you? You observe your surroundings to figure out which routes are dead ends and which might take you forward. You could use a compass by day and read the stars by night. As you continue, you pay attention to landmarks and get clues from those you meet along the way. By gathering and piecing together your knowledge of the landscape, you can make informed decisions to find the best route towards water. Water modelling is a lot like our traveller's journey. Victoria gathers millions upon millions of data points on our waterways and catchments each year to give us information on current and past conditions so we can make educated assumptions about the future. When we combine this data with our broader understanding of changes to the environment, we can start to ask questions. How will hot and dry conditions for years on end impact the amount of water we have available? Will the health of our waterways improve if we increase the amount of water we release into the environment? How will we share this finite resource equitably? Water modelling allows us to undertake vital work like the long-term water resource assessment and the sustainable water strategies, which help us to plan and manage water both now and for the future. Water modellers use the data to ask a broad range of questions about potential outcomes, giving policymakers the tools they need to prepare contingencies and ensure that Victoria will have access to the water we need. As we gather more data, improve our modelling tools, and continue to compare models to actual events, our models become more precise and more useful, just like our traveller who maps out their journey. Over time, as they make the journey again and again, gathering more information about the landscape, the map gets better and they understand more about the surrounding world. Water modelling is a vital tool that helps us to understand Victoria's water and prepare for the future. To find out more, visit www.water.vic.gov.au.
Is it okay? You found it interesting or so and so? Okay, let's continue. Okay, let's continue with the case study, not in Australia, Victoria, but in Greece. The Rhodope aquifer, actually in Greece. And initially we will see the conceptual modeling, data preparation, and then we will see the mathematical modeling, the calibration of the modeling, and use it in the management scenarios. So here we will see some steps that some information that we have to collect before starting the groundwater modeling. So the first absolutely necessary information that we need is related to the hydrogeological conditions in the aquifer system, the coastal aquifer. So we need this information because we need to construct the geometry of the aquifer, first of all. We need this information because we need to assume the type of the aquifer layers, if they are confined or unconfined layers, and also how many of these geological layers we would like to use in our model. Also, we need information related to model parameters, for example, hydraulic conductivity and how they are distributed in the aquifer, how they are distributed spatially. We need information, hydrological information for the boundary condition, what type of boundary condition we're going to use, and how we are going to assess the values of this boundary condition. This is also quite critical and difficult in cases. We need data and the methodology for the estimation of groundwater abstraction, which in many cases is a quite important water balance parameter for the model. And we have to define usually from the beginning, which is the simulation period we would like the model to run, which is the time step. And these are decided based on the desired analysis and also the available data, the available meteorological data or the available piezometric data. And to do all this, to collect all this information, it will be helpful and efficient handling of geographical and data time series data. So GIS and at least use very good use of Excel is minimum requirement for that. This is the Rhodope aquifer. It's a study area located in northeast Greece, as you can see here. It's approximately 190 square kilometers. It is a hilly area, but with gentle slopes and several surface hydrological features at the boundary of the area. As you can see, we have these lakes. At the east boundary is Lake Stonida. At here, the west boundary is Lake Stonida. Sorry, this is Lake Ismarida at the east boundary. This is Lake Stonida, which actually is a lagoon. So it has salinity. It's not fresh water, only fresh water in Stonida. We also have some smaller lagoons here at the southern boundary, the coastline also, and some small ephemeral rivers that drainage the insignificant, let's say, surface runoff during the winter. So here in this area, groundwater is the key source of fresh water, and irrigation is the key water use. The climate is Mediterranean, and the average annual precipitation is around 550 millimeters. So for this area, there is a research conducted in the past, a lot of research that provides with sufficient knowledge and data for the area. And all these data were collected during METSAL project to collect this data and use it for the construction of the conceptual model. So based on this data, we were able to identify two main aquifer layers, an unconfined phreatic layer at the top with an average thickness of 35 meters, actually with a constant thickness of 35 meters in the model, and another confined aquifer, which hosts the regional groundwater reserves. So between these two aquifer layers, in the middle, is we consider a semi-permeable layer, and at the bottom of the confined layer is the substrate, which is actually the impermeable layer that delimits the aquifer system. Okay. So we use the fifth law for simulating the three-dimensional variable density saturated flow in this aquifer system. We have the three geological layers, so we have four, yes?
Geological information.
Pardon?
Geological information.
What do you mean? Which are the geological
Yeah,
information?
what type of geological information?
Which type of geological information was used to construct the model?
Let's start with what is geological information?
What is geological information?
Geological formation.
Geological formation, sorry. Did you see somewhere here this?
Yes.
Yes, there we go.
Bottom left.
In the previous?
Yeah, the other one will show. But I cannot read.
No, the previous one,
Previous. Yeah.
the key in the map on the right.
The key map on the right.
There.
Geological formations.
Okay.
Okay. Probably we should ask the people who made the map, but it's different. You can see that we have alluvians, or it's different geological. Not sure I can find another word instead of formation. Different geological types. So we have the soil types. We have sandy soil or clay soil types, things like that. So sediment is a kind of it's another category. Are you a geologist or you are interested in the?
No.
That's just wondering what is geological formation. So it's different. Yeah, it's different type of rocks. Let's say. Okay. Which, as we can see here in this particular area, we have only two different geological formations. We have the alluvial deposits. Okay. The first one, which is here in the middle. And the sandstones, if I can recognize, actually have only two. So as we said, we use the fifth law to simulate the three-dimensional variable density saturated flow. We have three geological layers. So this means that we use four computational slices. We will see more details in the next slide. Here we can see the model area. And you can see with this line, we divided the model area in two parts. We did this because we would like to apply a finite element mesh in the model area before starting the computational. And we want a denser finite element mesh in the south part compared to the north part. because in the southern part we're expecting higher gradient of salinity variations. So as we have the sea here, okay. So we want a denser finite element mass here compared to the other one. And you can see the result here. You can see that we have more elements in the south part compared to the north part. So this is at the right is one slice of the finite element mass. In total, for the whole volume of the aquifer, we have around 3,000 mass elements and 2,000 nodes. Here we can see the configuration of the layers in the model. So we have the first layer, which is the unconfined layer at the top, 35 meters. We have the second layer, the intermediate, the semi-impermeable layer, which is 10 meters constant. We have the third layer, which is the confined aquifer, which hosts the key groundwater reserves. So, and based on available information, elevation information, in the first slice, which is on top of the first layer, and in the fourth slice, here at the bottom of the third layer, we can approximate the aquifer thickness of the third layer, and you can see here from the legend that varies for 40 meters to 140 meters, with an average thickness of 85 meters. Okay. So these are the model parameters that we used for the model. The horizontal hydraulic conductivity is as an average value 21 meters per day. But as you can see from this table, it shows the hydraulic conductivity first for each layer and also from the map. We actually assume not a homogeneous, a heterogeneous variation of hydraulic conductivity, right? And this is heterogeneous because it varies from here, from the map, we understand this. And it is an anisotropic because you have different values between the horizontal conductivity and the vertical conductivity. Okay. Also, we use different values for storativity, for specific storage and specific yield for the third from the three layers. And typical values from literature are related to the quality, water quality parameters of the model, the dispersivity and diffusion. And for the density ratio is this 2.5%, which is actually the difference between density of fresh water and salt water. Here we can see for the Rhodope aquifer that we have identified 3 freshwater inflow areas of the north, west, and south, and also 2 seawater intrusion areas at the bottom. And as you can see, even though there is a quite large area here that is connected with the sea, the aquifer is connected to the sea, at least we can see that they are very close. We didn't consider this as an inflow of seawater intrusion due to the extent of the geological barrier. Another parameter very important for the groundwater model is the estimation of the groundwater recharge. It's a key inflow parameter for the model. And the recharge depends on climatic condition, precipitation, evapotranspiration, and the soil types. It is sandy, clay, or loamy soil type. And is also very important because it is related to climate change scenario. So if you would like to use the groundwater model later in a climate change scenario, then you should consider very carefully from the beginning which method you are going to use to estimate the recharge. So the scientifically most rigorous way to estimate the recharge is to simulate the water flow in the Vado zone. But this is not very easy, requires additional effort and expertise. And also another problem is that there are not many groundwater models that are capable to simulate the recharge. So what we do, how we solve this problem? I have collected here 3 different options. One option is to use another model to simulate the Vadose zone hydrology, preferably with a model that solves Richard's equation. And an example of this kind of model is a Hydrogeological model or MIC model. Another option is to estimate the water balance in the Vadose zone, in the soil, or apply other similar empirical methods that use hydrological data and soil type data. And you can do this more easily by a spreadsheet or using a simpler model like SWAT. And the third option would be quite simple to estimate recharge as a percentage of the rainfall. Say just a constant value of rainfall, this is the recharge. You can have a variation of this percentage from month to month, or you can use a constant value for the whole year. And of course, in this case, it will be better to verify at the end the choice of this estimation through model calibration. Another very important parameter is to estimate the irrigation requirements, irrigation demands, because it is a parameter for the groundwater model to pump water from the aquifer to give it to the crops. So here in the Rhodope aquifer, we use this kind of data. We have the agricultural area and how this area, which kind of crops we have in this area, and how these crops are distributed in the model area. And based on this information, we estimate the crop irrigation requirements for the key crops, cotton and clover here, as you can see. And we also take into account the effective rainfall for the irrigation period, for the summer period, and also take into account the irrigation efficiency of the irrigation method that is used in this area. So based on all this information, we make all the calculations and we found that the groundwater abstraction as single number in the area is almost 50 million cubic meter of water per year, which is by far the most important water balance component for the area. Okay. Okay, that was about the conceptual model and the data preparation. Now we will see how we're going to calibrate the model and then use the calibrated model for the management scenarios. So let's first see, let's define what is a model calibration. So in general, it's a process to find a unique set of the model parameters that provide a good description of the aquifer system. And this can be achieved by confronting the model prediction with actual measurements. So we change the model parameters, we see the results of the model. We have also the observations, the field observation of the aquifer system in our case, which might be water levels or piezometric head in the confined aquifer, or even salinity. And then we try to find the best set of model parameters that the results of the model are more or less similar with the observations. Okay, so and then a calibrated model could be used for the management scenarios. In groundwater, usually because calibration might not be so trivial job to do, might be not so easy, we usually calibrate the model in steady state mode and then in transient mode. In steady state, the model does not consider the changes over time. So we don't have the concept of time in the model. Okay, but the data that we use in steady state could be defined as inflow or outflow rates. So we say that we have 50 millimeters per day that inflow in the aquifer system. Okay. In a steady state, we can calibrate some of the model parameters, like the hydraulic conductivity, for example. And in general, the steady state model help us to understand how the aquifer system works. Okay. Of course, it would help us more to understand that if we can compare simulated with observed parameters, piezometry, for example. In the transient state mode, we have a simulation period, we have a time step for the model. So the input data are usually time series that should cover the whole period of the whole simulation period. Okay. We can also calibrate some other type of model parameters like storativity, for example, the aquifer. And if the monitoring data are cover a quite long period, we usually divide the model period in calibration and validation period. And when we say calibration, we mean the period that we are trying to find the best model parameters. And in the validation period, we accept these parameters and we run the model and compare model results with observation and see what's happened. Okay, is it clear the difference between calibration and validation period? Okay. Hopefully, nowadays the modeling system have auto calibration algorithms, so they can do the hard job of the computer for us. But usually, a manual calibration through a trial and error procedure, change some parameter, run the model, see the results, change another parameter and do all the job, is usually a good start, especially for someone with not so many experience in modeling. And of course, the calibration procedure allows us to critically review the conceptual model. This means that if something goes wrong during the calibration and we don't like the results because they are not in agreement with the observations, we have the right, we can go back to the conceptual model and change something in the conceptual model because something was overestimated or underestimated. For example, an inflow of water, a lateral inflow, was overestimated during the initial estimations of the groundwater model. And we can see that running, for example, a steady state, we can see this very quickly. If something was underestimated or overestimated during the conceptual model. Okay, here we can see the steady state model and the boundary conditions in our case study, the Rhodope aquifer. You can see also the finite element mesh. Okay, so first of all, we see this lateral inflow here, 10 millimeters per day. You have inflow to the aquifer, 10 millimeters, here another 10 millimeters per day, and here is a less, you can see, flow due to geological and hydrological information which boundary. We also have the recharge at the top of the aquifer. Do you have a question?
Yes. How do you calculate this inflow?
Can I first finish this and then? Okay. We have the recharge at the top of the aquifer. And as we said before, this recharge is related as a percentage of precipitation. Actually, here is 5% of precipitation. We also have pumping from 90 wells, as we can see in all these, from these wells, with a constant abstraction rate, cubic meter per day per well. And this abstraction is only from the confined aquifer. Okay, it's not from the unconfined aquifer. But I would like to show this just in a single slide. So the recharge is on the top slide and the pumping is on the bottom aquifer layer, the third aquifer layer, as we saw before, and the inflows in all layers. And also here in these blue circles, close to the sea or the lagoons that we saw before. Okay, see they are in connection with surface. We can say that the hydraulic head is 0 meters, is at the level of the sea. Okay. So, starting from the beginning, this is a second type boundary condition, right? Because you have a lateral flow. You remember? So this is the second type boundary condition. This is the first type boundary condition. This is not a boundary condition, or the fourth type that we said before. Okay. And the charge is on the top of the unconfined layer. We can say that this is more or less second type of boundary condition. So how did we estimate this? We estimate this based, there are several ways to do that. It depends from the experience of the modeler and the available information. One way to do this is if you have piezometer data in several parts close to this boundary. You have water level measurements here and here. So you can estimate the hydraulic gradient. And if you have the hydraulic conductivity, you can get an initial estimation. You can also do it in another way if you know the geological formations that we showed before. And if you are experienced to translate these numbers, you can convert this to the boundary condition, or you can combine these two methods. Or this could be your initial estimation, and using the model calibration, you can find the final values of these inflow rates. Is this okay? Any other questions for this or for previous?
I have a question regarding the calibration. If we have more than one set of parameter values put for calibration, what's the best way to choose one set or another set?
So you mean that we have two different sets?
Two or more.
Two or more different sets of model parameters,
Yeah.
that they gave us the same result exactly.
More or less.
More or less. Okay. Each parameter, okay, we should know the physical problem and know which is the range of each parameter. So if, for example, the hydraulic conductivity, I will return, we are in 37. Okay. If, for example, someone told me that the hydraulic conductivity is 21,000, it would be an error. Okay. So it has a physical meaning, something meaningful. So this is also the same for specific storage, for all these parameters. So you have to know more or less which is the range that they are varying. Okay, that's the first. And this is also for the inflow and the outflow. But in general, in your question has also another, because there are different sets. That's true. That there are different sets that you could have exactly the same results. This is true. But if each parameter is varying inside the range that is acceptable, then any could be accepted. Okay. Someone else, I think, yes? Objective function, which kind of, you're talking about the case of an auto calibration parameter. Okay, we can use an objective function that minimizes the error between the piezometry. Let's say if we're trying to simulate piezometry, the difference between the piezometry that simulate and the piezometry that we measure. So there is a difference. There will be always a difference between simulated and observation piezometry. So if we try to minimize this difference, so that's the objective function.
This model kind of
Which kind of objective function?
can we use for example,
In this particular model, you mean? I'm not sure I understand. Can you give me an example of what you mean with kind? Which are the options? Oh, yes. Okay, yes. Obviously, when I say the difference could be the minimum, you should measure this with some statistical criteria. So mean square error, and this all of them. Fine. For this particular case, we didn't use an auto calibration. I have used for other models, not for groundwater model, for surface water model. Actually, it is an option that you can use only one of the statistical criteria, or you can use both of them. It depends on the type of the problem. I mean, if it is for a river flow, for example, you have to simulate peaks or low flow. Then you need also some additional statistical criteria. Simulate better this. Okay.
Some expensive.
Okay. I'm not sure how to see these questions.
Excuse me, may I ask my question orally?
Oh, yes, of course.
Okay, cool. Thank you. Yeah, I have a question about the time that you mentioned we can use the unsaturated flow models to get the recharge, like Hydros or Mike. In that case, what kind of bottom boundary condition we have to use for those models?
What kind of boundary condition you said?
Bottom boundary condition, yeah. And usually these models are one-dimensional.
So you have to use, you need the information of precipitation and evapotranspiration. So one boundary condition is the precipitation that goes to the top of the aquifer, actually, sorry, to the top of the soil. And the bottom boundary condition would be the recharge, which is going to be used to the groundwater model.
But I mean, if the phreatic water level comes to nearby the surface of the soil, then we have to use that as a boundary condition too, or it should be the answer of the groundwater model.
Okay, it depends. Depends. I mean, if the unsaturated, if the water table in the unconfined aquifer is 50 meters from the soil surface, then it will be very difficult to have an unsaturated model, Hydros model, for 50 meters. So in this case, we should have other options to use, for example, a free drainage option from the bottom of your soil model, the Vadot zone. But if the water level of the unconfined aquifer is quite high, let's say a couple of meters from the soil, then you can use it as a boundary condition to the soil model, to the Vadot zone model.
Okay.
Okay. Is there any other question from our line friends? Here? Okay. Okay, this is a steady state model and the boundary condition that we said before. So we run the model, with these conditions. And here we can see in this diagram how the water balance the aquifer is formulated. So you can see that we have quite huge inflow into the aquifer. Note here as Dirichlet boundary condition, which is actually due to this condition that we said before. Okay. So we have inflow from here. This is Dirichlet boundary condition. So actually it's a seawater, saline water that inflows into the aquifer, right? Can you get this? No. Okay. This is the configuration. This is the boundary condition. So we have first type of boundary condition here. 0 because, okay, it is the sea level. Here at the mountains, you have some freshwater lateral inflows. Second type boundary condition. Okay, we have some inflow rates. Recharge, another inflow at the top of the unconfined layer, and at the confined layer, we have all the three layers in the system. We have some pumping. So water inflows, outflows, inflows, outflows. We don't have the concept of the time. So we put it here, let's say that we make all the calculation for a steady state. This is the result, and this is how it forms. So what we get from here, this is the inflow. The head is 0 here, so the model tells us how much water inflows into the aquifer. And because we know that we are at the sea, if we run also the transport model, is going to be salinity, that inflows, saline water that inflows in the aquifer. These are the two inflows, the Neumann boundary conditions, is fresh water that inflows in this boundary, and the distributed sink source is the recharge from the top. And since we are in steady state mode, this means that all these inflows of water, all of this is water, should be equal to the volume water that extracted from the aquifer. And you see that the water is abstracted by the pumping wells. You can see at the bottom the imbalance, the error of the model, let's say. So since we have a lot of water that abstracted, the model tells us how much water is inflowing from the bottom boundary condition. That's the key answer that we take from this model in this case. Okay, we will see some more results here. So here, with this steady state model, with this boundary condition, that was the water balance of the model, and here we see some results. So we run the model, we keep all the parameters the same, and we just change the recharge on top of the aquifer. So in the first case, 5% of precipitation, 7.5, and 10% of precipitation. And as you can see here, we take 3 different maps. These are hydraulic head maps, isometric maps, distributed in the aquifer system. Is this more or less clear? Okay, so we see here the hydraulic head distribution. We see that in each case, in all the cases, the hydraulic head here is almost 0. They have the same, take the same result. Because from the first type boundary condition, it is imposed to the model, and we say that the hydraulic head should be 0 here. So we don't have great changes here in all the simulation runs. But in the middle of the aquifer, or on the north part of the aquifer, as you can see, we take quite different results. And particularly for the 10% of recharge, we see higher values of hydraulic head. We see minus 14 in the middle, compared to minus 18 here. Why we see higher values in the 10% of recharge? Can someone tell? It's very simple. Yes? Yes, Maria? recharges more, so we put more water in the aquifer. So if we put more water in the aquifer, so we have a higher, okay. But what we see also in all these three different simulations is the hydraulic gradient is negative from the coastline to the center. Can you see that? Yeah. Okay. Good. Perfect. So here we can see the effect of hydraulic conductivity in hydraulic head. We have all the parameters the same in all three different runs. It just takes hydraulic conductivity 5 meters, 10 meters, or 15 meters. We see some difference here. Am I right? So close to the boundary, we have also the 0, but here we can see minus 40. To the other case, minus 15 or minus 12. Great difference between modeling results. Can we explain why they are different? Changing just the hydraulic conductivity, keep the recharge 5%, keep all the other parameters the same. You can see that we take enormous, quite different results between the three different runs. Okay, this could be explained by the flow equation from mathematics. This could be explained. So you can see here the flow equation that we saw before. I just add another component here, the Q pumping, since we have pumping here. The previous version of the equation was quite simple. And we said that we are in steady state. So we don't have time. So here we see the derivative of time in this part. So since we are in steady state, these two terms should be 0. Okay, so the left part of the equation is constant with the QP. Okay, with the pumping. So it's a constant value. So from the right side of the equation, obviously as hydraulic activity increases, the gradient of hydraulic head should be decreased. Am I right? Okay. And in this particular model, this is not general and it could be for all models, but in this particular model, that we have a first type of boundary condition to the sea, and we say that the hydraulic head is 0 here. This means that the hydraulic gradient, we said that it is the difference for a particular distance, it is the difference of hydraulic head between 2 points, is lower in case that hydraulic conductivity is 15 meters per day compared to the lower hydraulic conductivity. That was very deductive. We learn a lot from this, but what we actually gain from this interpretation is that we managed to calibrate the model quickly. Okay. Here we can see another other 3 runs of the model. We have the same value of hydraulic conductivity, the same value of recharge, all the parameters are the same, and we only change pumping, the pumping from the wells. So here is the actual pumping, what is happening, 100%. Here we have less pumping, 75 and 50%. And we see different results, obviously. And as we abstract less water from the aquifer, we have a higher hydraulic head in the last case. Of course, this is very difficult in terms of to manage to convince people and to decrease the pumping 50%. That's quite difficult to achieve this specific case study. But let's say that we will do this. You can see that in the 50% pumping, the hydraulic head is almost equal to the boundary condition, which means that we don't have seawater intrusion at all. So we don't have a negative hydraulic gradient. While in this case, we have negative hydraulic gradient, so seawater inflows as the groundwater is flowing from the 0, I forgot probably to say that groundwater flows from the higher values to the lower values. obviously. Okay, that was some quick management scenarios, and we said about the calibration of the model. So in the left map here, we have the hydraulic head distribution, we have the modeling results, and in the right map, we have actually the measurements, the observed head in the aquifer. So we have to compare this. One way that speeds up the model calibration is to create this sloping line comparative graph that we have in the one axis, the simulation hydraulic head, in the other, the observations. So we see that these points here, as we see that these points are close to this line, this means that the model is calibrated and is sufficient. If the point deviates from the line, it means that we have to calibrate it more the model and more effort is needed. Okay, apart from just seeing the results, we usually use some statistical criteria. Here we have the correlation coefficient is 0.83, which is quite good. So we can say that in this case, the model was calibrated sufficiently. In the transit model, we use the initial condition of the steady state model. We run the model for 6 years with an initial time step of 1 day up to 30 days. We convert all the input data in forms of time series, as you can see with these graphs, and I will run before, of course, we have to finish. And then in these control points of the transit model, we compare model results with observation. With the points are the model, the observations with the black lines, and the colored lines, sorry, with the black points are the observations, and with the colored lines are the modeling results. Different, we see they are different because we run the model several times for different value of the specific storage parameter. So we used a uniform value of the specific storage, and we have these graphs. So we saw from these graphs that the model results are not very close to observations. In most of the cases. This is just 2 examples. So, but from this exercise, we were able to actually create this specific storage coefficient map in the model area, okay, based on the previous exercise, and then run the model again. Using a simple data, this one, we were able also to calibrate the model for the transient state. For the transport model, as we said before, the concept of total dissolved solids that we used. You can see here that seawater, we have a boundary condition of seawater 35 milligrams per liter as a boundary condition here in the sea. And in Lake Lagoon, Pistonida, we have a boundary condition that varies from for some nodes is 8,000 milligrams per liter, and from some other nodes is 15,000 milligrams per liter. So the initial condition for the model, for the transport model, was based on field measurements, and we ran in this case simultaneously the water flow and the mass transport model. Okay. So we run the model, and here we can see the salinity distribution after 6 years at the right, and how it was at the initial condition. And we see, if we take, for example, this line of 10,000 milligrams per liter, but we see that after 6 years, it's almost 2 kilometers coastline, instead of 200 meters that it was in the initial condition. And here, will not see, there are some videos that I didn't activate it from the beginning. Here we can see in No? Pity. Okay. No worries. It was some video that's always showing every 6 months how the hydraulic head is changing and how the salinity is changing for the whole simulation period of the 6 years. But that's okay. That wasn't so important. So now that we have seen the physical-based model for the management of a coastal aquifer, we may ask to ourselves, and actually I'm asking you, if you think that they are useful. Do we really need them for the management of the coastal aquifer? Yes, no, and why? It's just opinions, it's not. Would you like someone to say his opinion? Do we need them or we don't need them? Or which are the problems for using this kind of models for the coastal aquifer management particularly? The data, we don't have data. Pardon? How good are the results if they say the truth or the?
Yeah, maybe you can have some problems inside, documentation, situation that you can know.
Okay, good. Yes.
You have the data vary with time,
Have the data?
how the data changes time.
With time. Okay, so it's difficult to implement this in the model, it will be a problem. So these are some problems, but in general, are they useful? Do we need them for coastal aquifer management, or we can do something else? That's a question. And which is this something else? Do we need this kind of model, or we don't? What do you think?
We need if we are able to model our case study.
So we need them if for a particular aquifer we have the appropriate data to construct the model, something like that. You mean. If we don't have the data, then we should do first collect the data.
If I can build my model, but I know that it's only an example.
Exactly. Okay.
At the same
You're
time,
right.
it would be interesting, like combine the physical-based method with the not just partial information. So, gene combined by our data, extend our data set, and after data.
So having some monitoring data and use the model to enlarge the database, for example, something
Get
like
some
that.
information, you have data, sparse data in your domain, and you can, I don't know, use like co-bridging model, target model to extend your data set as well. To give you a physical business.
But my question is quite simple, yes or no? Do we need it, yes or no? So it's okay, we can, what do you think? What's your feeling? Do we need for the coastal management? Yes?
I think it's useful, of course, but on the other hand, we need to be careful when we use numerical models.
Okay.
Because it's supposed to be just a support tool. For instance, it will allocate injection bottles for management and charge in order to help the freshwater seawater interface.
Okay.
However, I wasn't able to apply SWI tool in the model because it's a regional scale. I also forgot the developers. Yes, I'm still
So a quick answer is that we need it, but we should be careful. Something like that. It's the point of view. Okay, let's say my point of view. So what we get from this model? Actually, the information that we get from this model is hydraulic head and salt concentration maps or time series. I think this is the information that we get from this model. We don't take anything else. This is the first objective conclusion, let's say more or less. In some cases, this model could be valuable for scientific and educational purposes. You remember that we saw the example with the hydraulic conductivity. That would be something, okay, important that we get from this model.
Also the maps with the pumping rate, I don't know, but in
Okay.
for example, in a little lab with farmers, you can show them the effect of reducing.
Similar, very quite to what we are saying now is this third bullet that we say that this model could, and actually they should be used by the water management directorate, even though to issue water use licenses. Okay, they could be used this model. And of course, this model could be used to evaluate water management scenarios, and not only to evaluate, but to quantify. That's the most important that we can do with this model. We can quantify what we are saying as scientists. So there are some problems. You said a lot of them before. They are difficult to use, and these kind of models, they are even more difficult to use. But in this case, this will not be an issue if there is experience, well-trained, and well-educated scientific personnel. This will not be an issue. This is something that we can overcome this problem. Another problem is the uncertainty of the model results, as I said before, but this could be also solved. We can address this problem if you have a sufficient calibration and validation of the model. And also, we can do this for a period of time, for 3 years during a PhD or whatever, and then we return back after 10 years to calibrate and validate again the model if we have new available data. So it's not a job for a month or for a year. It's something, a lifetime job. Actually, you can take this job from someone else and improve it. Okay. So here we can see some management scenarios for coastal aquifers in general. We will divide this in a management scenario to protect an aquifer that already face seawater intrusion problem, and we can use model to evaluate this scenario. So one of these measures. So one measure is to reduce pumping in a more logical percentage, not 50%, something like that, that feasible to implement. 10% or 20%, something like that, to allocate the pumping, to change the location of the well, or change the pumping rate without reducing the pumping volume, the volume of the water that pump. Other measures is to increase the natural discharge, but this is not trivial, and hydrogeologists will say to us that this is not very easy to implement it in a real aquifer. Also, to use freshwater recharge well is another measure to protect an aquifer with a problem, coastal aquifer with a seawater intrusion problem. But in this case, also a problem would be that we have spare available freshwater to use to inject into the freshwater aquifer, but in some cases could be used to construct lower permeability barrier to block the seawater underground with concrete boreholes, but this also could be efficient only in an aquifer with a small extent, obviously, to create positive or negative hydraulic barriers. And when you say positive hydraulic barriers, we mean to inject fresh water close to the coastline in some boreholes, or to abstract seawater, that's the negative hydraulic barrier, to abstract seawater close to the coastline. And of course, we can use the model for scenarios to evaluate water resources planning for an aquifer that don't have a problem at the moment, but maybe it will have in the future. So we can use the model to assess the effect of the increased abstraction, or use it to climate change scenario. And climate change scenario, I suppose it's understandable for everyone that in climate change scenario, we have a reduction, the charge is reduced, and the irrigation demands are increased due to the increase of the temperature. Okay, this is the temperature is increased, the evapotranspiration is increased, and the irrigation demand are increased. So for the conclusion is, for the end of the day, as we say, that for the management and protection, not only for a coastal aquifer, but for any aquifer system, we need a policy, sustainable management goals. We need a calibrated groundwater model, and in this case, for our case, a flow and solute transport model, and a well-established monitoring network. Very quickly, some computer codes for modeling seawater intrusion. Just 3 of them. There are a lot of other that they do the same job, but we will stay in these 3. So Sutra was one of the first variable density flow model that simulates saturated, unsaturated groundwater flow with solute and energy transport. As a numerical method, it uses a hybrid of finite element and finite difference method, and can simulate 2-dimensional and 3-dimensional problems. Public domain software developed by USGS. T-flow is a model that is giving more attention to the finite element analysis method. Okay, it can simulate saturated, unsaturated flow mass and heat transport in porous and fractured media in 2 dimensions and 3-dimensional problems. It is a commercial software provided by DHI. And SeaWatt, which is a model that actually combines the capabilities of mod flow and MT3DNS. So it's a model that simulates saturated variable density groundwater flow of multi-species solute and heat transfer using finite different methods in 2 and 3 dimensions. Also a public domain software by USGS. These are some models, some books for those who would like to study further the topic. Thank you very much.